Here we're told to graph a quadratic function. We know it's a quadratic because our largest exponent is a 2. And we have x squared. Now please don't forget that standard form is your ax squared plus bx plus c. Forgive me, that's a little difficult to write on the iPad. So our a value is always in front of x squared, our b value is always in front of x, and our c value is always a number not attached to a variable. You'll notice that we didn't really have a b value attached to an x. There is no x value. So we actually have our a value is -1. Since there's no x without an exponent, our b value is 0, and our c value is -1. So at this point, we can find the axis of symmetry, and because I know my b value is 0, I automatically know my axis of symmetry is going to equal 0. So our axis of symmetry, that should be a 0. Like I said, sorry guys, it's difficult to write on here, is x equals 0. So that's going to be a vertical line going through the x-axis at 0. And remember, I always like to make it a dotted line. I'll label that x. I like to make it a dotted line because it is not actually part of the parabola. It's just a reference point that we're going to be using. It's a great reference point when we're going to find the vertex. Remember, we find the vertex by taking our axis of symmetry and plugging it into our function. The reason why we're doing that is because the axis of symmetry and the vertex are both in the middle of the parabola. So if we plug it in, we get y equals -x squared minus 1. Please note how I put a set of parentheses where x goes. Whatever number goes in here, that negative has to stay on the outside. That squared value does not affect that negative at all. So we actually end up getting, we plug in 0, we get -0 because 0 squared is 0, minus 1. Well, there's really no such thing as a -0, so we just end up getting -1. So our vertex is 0, -1. Please don't forget, once you do that step, I want you to label that vertex. Doesn't have to be perfect. Just make sure you show that because that shows that that's the middle of the graph. If you're just finding random points, it's not going to help you if you don't know where on the parabola you're graphing. So I'm going to plot this point at over 0, down 1. Always graph your points from the origin. And there's my vertex. I'm actually going to label that vertex. The next step that I usually have a lot of people write is our y-intercept. Something that we had discussed is, well, y-intercept is our c value, which is -1. But if you look at our graph here, our y-intercept is the same thing as our vertex. Our vertex is the point that crosses through the y-axis. So the problem here is we're stuck. We don't have any other points to go from. And I did not mean to write that circle around there. Sorry, folks. I meant to do this guy right here, the little laser pointer. So our vertex and our y-intercept are the same point. The problem is we need more points. We need additional points for our graph. So what we're going to do, we're going to create a table. The purpose of our table is to get more points. The reason why we can't use this y-intercept is because our axis of symmetry is on the y-axis. Is it always like that? No. Sometimes it is and sometimes it isn't. It depends on the b in our original function. So we're going to create a little table, and let's pretend we have to do a minimum of 5 points. I'm only going to find 2 points. The reason why I'm going to find only 2 points is because whatever's on one side of my graph, I can easily reflect it to the other side of my graph. And I can do that without showing any work. So I'm going to plug in numbers 1 and 2 for x, simply for the fact that numbers 1 and 2 are closest to the axis of symmetry. They're both positive numbers, so I'm going to get hopefully smaller numbers as a result. And I'm going to get -x x squared minus 1, negative x squared minus 1. See how I haven't plugged in anything yet? I'm actually going to see about using a different color for that. Let's see. I don't think it will let me use a different color for that. No. Alright, I'll do that in red. So I'm going to plug in 1 and 2. And what we're going to do is we're actually going to do our exponents first. You always do exponents before multiplying. So 1 squared is 1. Negative 1 minus 1 is negative 2. 2 squared is 2. That gives us negative 4. I'm sorry, 2 squared is 4. Negative 4 minus 1 gets us negative 5. We're going to actually graph these 2 points. We get 1 comma negative 2, and we get 2 comma negative 5. Those 2 points are here, so we go over 1 down 2, we get a point right here. And we get another point at over 2 down 5. We're going to use this axis of symmetry to reflect these points to the other side of the axis of symmetry. And I'm going to just draw a little X to symbolize reflection. Then from there you can draw your parabola. A few things that I do want to cover before completely finishing the video. Because at this point we're pretty much done. We've completely graphed our parabola. We used a minimum of 1, 2, 3, 4, 5 points. I want us to take a look at this original right up here. So let's take a look at our original function. I'm going to box that in purple here, this light purple. That's our original function. The number in front of x squared determines a lot about the graph. It determines whether it's skinny or wide, whether it's face up or face down. In this particular case, it's just a negative without a number, so we assume it's negative 1. Negative means it's going downwards. So it opens down is what we typically say. So this graph is going to open down. This is our y-intercept. It is the same thing as our vertex because our b value is 0. So we know that it's going to go through negative 1. So because our b value is 0, we know that, well, b value means our axis of symmetry is 0. That means our y-intercept will be the same thing as our vertex. So we automatically know our vertex would be there. Technically, we could sketch this graph, make it not terribly accurate, but we can get an idea of what it looks like based on those 2 pieces of information.